Okay, in this video, we continue with chapter 6.4, and we are going to cover similar matrices in this part of the video. In the earlier video, we saw transition matrices. So we know two square matrices A and A prime can be related through this equation here, where A prime equals P inverse AP. And so if we have this relationship with this transition matrix P and its inverse, then we say A and A prime are similar matrices. And that's just what the definition of the similar matrices down here says. A and A prime are similar when there exists an invertible matrix P such that this relationship holds, that A prime equals P inverse AP. So if A prime is similar to A, then it's also true that A is similar to A prime. So similarity goes both directions. And so this theorem, 6.13, gives us three equivalent properties of similar matrices. And this is handy because if you find one property, then the other two properties are also true. All right, our first property says that A is similar to itself A. And in this theorem 6.13, we're going to let A, B, and C be square matrices of order n, meaning they're all n by n matrices. And of course, it makes sense that A is similar to itself because you can use the identity matrix. If A is similar to B, then B is similar to A. That's our second property. And then our third property is saying if A is similar to B and B is similar to C, then A is also similar to C. So let's take a look at the proof of these properties. So property one here follows nicely using the identity matrix. So we can say, well, A equals IN, the n by n identity matrix multiplied by A multiplied by the n by n identity matrix again. Our second property here, we start with A equals P inverse BP because we know in this second property that A is similar to B. So then we want to rearrange and get B by itself to show that B is similar to A. So we do that by multiplying P on the left side and P inverse on the right side. And we're able to do that as long as we're consistent with our matrix multiplication. And then over on the right side, the P inverse and the P multiplied together are just the identity matrix. So we end up with B isolated on the right side. And so then we can say, oh, let's just call Q P inverse. And then we've got this relationship Q inverse AQ equals B. We had to call Q P inverse because we wanted to have a relationship such that it's inverse matrix A multiplied by the matrix itself. So that's why we define Q as P inverse. And our third property, we know that A is similar to B. So we can say, well, B equals P inverse AP. And then if B is similar to C, there's some other matrix that we'll call Q, such that C equals Q inverse BQ. So then we can say, oh, well, C is Q inverse BQ, but we can replace B in here with P inverse A multiplied by P. And then we can say, oh, well, PQ can be pulled together by matrix properties with the inverse outside, and PQ over here can be pulled together. So this matrix PQ is the transition matrix that's showing us that A is similar to C. So to prove this third property, we just made use of our matrix properties. So let's take a look now at two examples. So in our first example here, we're going to let A be the matrix for T relative to the standard basis. Here's our matrix A right here. So since we are in R3, our standard basis is good old, 1, 0, 0, 0, 1, 0. We call this the E1, E2, E3, and 0, 0, 1. Okay, my Apple Pen's not writing so great, but hopefully you can see the gist of our standard basis in R3. And then we're going to say, okay, B prime is this other set of basis vectors, -1, 1, 0, 2, 1, 0, and 0, 0, 1. And so we want to find the diagonal matrix A prime for T relative to the basis B prime. So let's take a look at our solution. We're just going to go through the regular calculations, and A prime ends up being diagonal. So you don't have to do anything special to diagonalize A prime. So the transition matrix from B prime to the standard matrix has, there's like a line here, has columns consisting of the vectors in B. And so here's matrix P. So we just take our B prime vectors and correspond them with the columns of P. And then using SIMPy or calculations by hand, we can get P inverse here. And then to find A prime, we multiply P inverse. So we're moving over to this side of the screen. P inverse AP. And so that's what we got right here. P inverse A and P. And so that gives us our matrix A prime right here. And A prime by default, by the construction, is a diagonal matrix here. And then here's a next example. We're going to look at two little proofs here. So the first proof is to say, consider the matrix equation B equals P inverse multiplied by A multiplied by P, where P is a transition matrix. Then we want to prove that if AX equals A, then P inverse P inverse multiplied by X equals X. So if AX equals X and B equals P inverse AP, then we get P multiplied by B is going to be A multiplied by P. Does that make okay sense here? Let's write out that step. So P B here is going to be P inverse AP. So that's why we're able to say PB equals AP, because the P and P inverse cancel each other out. All right, now if we multiply by P inverse on the right, we're just going to add A, because P inverse multiplied over here by P is going to cancel out. And so then we have B multiplied by P inverse times X equals AX, which we know equals X. So we just showed this relationship right here, that P inverse equals A. And then we're just substituting that in. All right, a second proof for us to look at. We're going to prove that if A and B are similar matrices, then A transpose and B transpose are similar matrices. So we know B is P inverse AP by definition of A and B being similar matrices. Then B transpose is a transpose of that. And then by properties of transpose and matrices, we know we get to apply the transpose, and then the order of the multiplication switches around, if you remember back from earlier chapters. So we end up here with P transpose A transpose multiplied by P inverse transpose. And then we know also that we can flip the exponent order with transposes and inverses. So we can rewrite this as P transpose A transpose P transpose inverse. And so that's showing that A transpose and B transpose are similar, because this was B transpose over here in our equality. So we have B transpose equals this relationship with A transpose on the inside, and that's a similar matrix relationship. Okay, so in the group work, you will be doing some practice with these chapter 6.4 similar matrix calculations.